So chapter 6 is all about trig fun with trig. You can replace the word fun with proofs. Yeah. So in that sense, fun and proofs are identities because you can replace one with the other. They're synonyms. And that's what an identity is, remember. It's a mathematical synonym, meaning it's an expression that is equal to something else that physically looks different phenotype, but has the same genetic makeup, the same genotype. And so you can replace one expression with the other without a loss of generality. All right? Bless you. So we're going to be learning and memorizing some fun identities in this section. Fun, of course, being short for fun. The mental, right? The mental. All right? So let's quickly review some types of equations, because there are several types of equations. You first of all have name equations. What's a name equation? Yeah, very good. Like if you have the expression 2x minus 4, you don't want to refer to 2x minus 4 constantly as, hey, 2x minus 4, what are you doing, 2x minus 4? Bless you. And you don't want to just say, hey, you, because then all the functions look, right? So you give it a name, like f of x or g of x. Now, the name of the function would be f. X is just the function notation that defines the independent variable. And this is still the part that some people have troubles with on free response, right? Where it says write an equation. I usually bold the word equation, and some people just write the expression. And of course, you lose points for that. So a name equation is simply that. It refers to an expression by name, so you can refer to it now as f. F. That's all you do with name equations. Conditional equations are the ones that you probably have a lot of experience with. What's a conditional equation? Yeah, you said the key word solved, right? You're reading 2 as well, same thing. A conditional equation equates to expressions like x and x squared. You set them equal. Now, is that a true statement? Not always, right? It's only true under certain conditions. That is, for certain values of x. So that's what you do with a conditional equation. You solve. They might have more than one solution, but they're going to have a finite number of solutions. All right? Then you have something called a contradiction, and that's an equation that's never true, like 2 equals 1, right? We talked about that the other day. We call that identity theft. That is not an identity. That is never true. 2 does not equal 1, okay? And we show a contradiction kind of like 2 rams butting heads. We draw 2 arrows ramming heads. It means it's irreconcilable. It's not true. So what are some contradictions? Well, the square root of negative 1 minus x equals ln of x. It looks like an equation because it has an equal sign and it has a variable on each side. But if you tried to solve this for x, you would find that the number of solutions that satisfy this equation are precisely 0. There are no solutions. There are no values of x that make this true. So this would be a contradiction. In algebra 1 or 2, if you started with a variable equation and you were trying to solve it, you would know that it was a contradiction if at the very end your x's went away and you ended up with something that was an untrue statement, like 5 equals 4 or 0 equals 1. Then you knew there were no solutions, contradiction. And then you have identities. And identities are kind of like the opposite of contradictions. They are equations that we said are true for infinitely many values, not 0. They are basically mathematical synonyms. Now, they don't have to be true for all real numbers, but they have to be true for all values in the domain of each function. So in other words, pick any value of x. If you plug it into both sides and you get an output on both sides, it's always going to be the same output. And that's what we're going to focus on in this section, an equation that's an identity. All right, so it equates 2 equivalent expressions. So let's just jump to the first group. The first group of fundamental identities, which means basic identities, that you're going to have to memorize, we call the reciprocal identities. And believe it or not, bless you, you already know these. You don't have to rememorize them because you already have them memorized, right? Here's what they say. They say that sine of theta, and notice we're going back to theta, sine of theta is the same as what? 1 over cosecant of theta. Did we already know that? Yes, this is how we found the cosecant ratios from the unit circle. Actually, the second one, really, which is equivalent. Cosecant of theta by the same token is 1 over sine of theta. So cosecant and sine are reciprocals of each other. Okay, they don't fight over who is the reciprocal any more than Tyler and Cade fight over who is their brother, right? Or Cooper and Caden fight over who is the brother. They are each other's brothers, right? So sine and cosecant are reciprocals. So what does that mean? That means that if you're working with a sine of theta in an expression, you can replace it with 1 over cosecant, and nothing's lost. It's exactly the same. It's equivalent. Now, let's talk about the domain. Is this going to be true for all values of theta in the whole wide world? What's the domain of sine of theta? All real numbers. So any value of theta on the left is going to produce an output. What is the domain of cosecant of theta? Is it all real numbers? No, cosecant has vertical asymptotes. Also, values where cosecant is equal to 0 are going to be undefined because 1 over 0 is undefined. But for all the other values of theta, when you plug it into the left and get an output, when you plug it into the right and get an output, they are going to be what? Not different, but same. Identical. That's a great word. Identical. Ergo, the name, identity. All right, so help me out with this one. Cosine of theta is equal to what? 1 over secant of theta. And similarly, secant of theta is 1 over cosine of theta. Tangent and cotangent are reciprocal, so tangent's 1 over cotangent, and cotangent is 1 over tangent. So there you go. Those are called the reciprocal identities. Memorize them if you haven't already. Okay, the bandwagon's getting pretty crowded, but we'll make room for you. It's the place to be. It's popular. All right, example 1. It says, using the definitions of the trig functions in terms of x, y, and r, prove that tangent of theta is 1 over cotangent of theta. So you have a healthy, natural skepticism, right? You should. You should question things. Curiosity. So you don't want to necessarily take my word for it that tangent of theta is the same as 1 over cotangent of theta. Because what if you're someplace where it really matters and you do this substitution and I've been lying to you and now you're the one who gets laughed at and embarrassed? That would be unfortunate, right? You don't want that to happen. So I'm going to prove it to you. And that's what this whole chapter is really about, proofs. Now, to prove a fundamental identity, there's not really many ways to do it. Fundamental means what? Basic. Can you get more basic than basic? Not really, okay? So to prove a fundamental identity, we're going to have to go back to the definitions of the trig functions. But what you're going to see moving forward is when we start proving bigger and better identities, we're going to be using the fundamental identities themselves as the building blocks of the proof. But to prove something that is fundamental, you have to go almost subterranean. You have to look at the genetic DNA. So I'm going to talk you through how we're going to be proving things. All right? Here's what you're going to do. You're going to first draw a line down the equal sign. And what that is going to do, it's going to keep you from cross-contaminating each side. Because unlike in a conditional equation, where you can multiply both sides by 5 or add 3 to both sides, that is not how you prove something. What you have to do is treat each side as a separate expression. And you have to work with the expressions independently. And it doesn't matter which side you work on, but at the end, on the bottom line on both sides, the bottom line should be exactly the same. And if you can get the bottom line on both sides to be exactly the same, you have made this logical loop of equivalent ideas, and you've proved it, all right? So I'll show you how to do that. Whew. Which side should we start on? It doesn't matter. Tangent of theta or the 1 over cotangent of theta? Let me establish some early criteria here. Is it easier to build a house or to tear a house down? Tear a house down. How do you tear a house down? By breaking it. How? You like just insult it constantly until it goes, oh, and it breaks? An excavator. Right. You don't really need a lot of technical knowledge, a lot of know-how, or even a lot of tools to tear down a house. Really, you could do it with a sledgehammer and just a lot of energy, right? Unrelenting energy. You can go wild. You can go crazy. You start swinging away, and it'll tear down. But to build a house, can you build a house with Just a bunch of raw energy and a sledgehammer? No, no. You have to construct something. And so it requires a lot of different tools, a lot of different know-how, okay? So it's easier, essentially, to tear something down than it is to build it up. That's the point I'm trying to make. Would you agree? Okay. So with that in mind, you want to start on the side of the equation that has more information. So you could tear it down. Which side has more information or looks more complex? The right side. Good. Because it has 1 over. That's more information. Now, ultimately, it doesn't matter which side you start on, but it's just easier to start on the side that looks more complicated or has more information. All right, so here's what we're going to do. We are going to replace cotangent of theta with its definition in terms of x, y, and r. So help me out, because I forget. It's x over y. Good. Now, did you do geometric proofs in geometry? Did y'all do that? Were y'all fortunate enough to do that? In geometric proofs, you probably, once you did one thing, you probably had to write off to the side the reason why. Like there was theorems, right? Okay? So this would be definition of cotangent of theta. I'm going to do that here. Truthfully, though, ultimately in this class, you're not going to have to write the reasons. But if you skip a step in the proof, it's going to be wrong. Because in a proof, the process itself is the product. That's what I'm grading. So at any point, if there would be like a reason or a theorem for the reason something happens, you would need to show that step. You wouldn't have to write the reason, but you would need to show the step. Okay? Now what could I do on the right side? I have a complex fraction. And anytime you have a complex fraction, you're like, hooray, hooray, because you know exactly what to do next. And that's to eradicate the complex fraction. So there's a couple of ways to do it. You could do state change flip, or you can multiply, like I taught you earlier, multiply by LCM over LCM of your miniature denominators, which is y. What would y'all want to do here? Doesn't matter. State change flip is nice because you have a single number divided by a single fraction. So that's going to be not 1 divided by x over y, but 1 times y over x. And what would the reason be? I'm just going to put property of division. Now, do you need the 1 there? Yes. This is why I'm saying if there's a reason for something, you want to show the step. Okay? Now, what is 1 times y over x? Y over x. And the reason would be identity element of multiplication. 1 is the identity element of multiplication. 0 is the identity element of addition. All right? And now, finally, y over x is what? It's the definition of tangent. So now we'll put tangent of theta, and the reason would be definition of tangent. Now, aside from the color difference, and maybe the way it's the script, the font, we have tangent of theta on the left and tangent of theta on the right. Are the two sides exactly the same now? Yes. And so we've completed the proof. When you're done with the proof, here's what you could put. On the bottom right, typically, mathematicians write Q, E, D. And it's basically a way to say the end, like at the end of a story. What does it stand for? Quotations, Erasmus, doofus. I don't know. That's not right. Anybody have an idea what it stands for? It's Latin. Anyone know Latin? Any Latin scholars in here? You did guess Latin? That's good. It stands for quid, erat, and this is why the Latin language is so cool. Demonstratum. That's a cool word. Demonstratum. Quid erat demonstratum, which translates into, bless you, that which has been, and it's almost an English cognate, demonstrated. That which has been demonstrated. It's basically the Latin way of saying, I did it! I did it! I showed you how I did it. I did it, right? Okay? That'd be cool if Dora did the Quid erat demonstratum song at the end of every show, right? But that would be Latin Dora. Right? Not Latin American Dora. Quid erat demonstratum. It means I did it. Okay? Sometimes you might see also, if you read math journals, at the end of a proof, instead of QED, they put like a tiny little square box, which is the concise, perhaps snooty way of saying, I did it! Huh? Oh. Well, I guess I'm kind of giving you a choice. Do you want to put QED with a dash? It's kind of like signing off at the end. Or you want to put a little box. Or to make this chapter more fun, come up with your own sign-off line. My favorite is sizzle. Oh, I love that. Right? Sizzle. Burn. Cooking with oil, right? Oh, man, I'm on a roll. Sizzle. If you like it so much, go ahead and just sign it like a piece of art. That's my signature, by the way. Don't steal it. Okay? Identity theft hurts. Not talking about you stealing it. I'm pointing to you because you've had your identity stolen not once, but twice. Okay? I don't care. If you want to put bring it on, I'm fine with that. Or simply from the Charles Dickens play Oliver, more please. Okay, more please. You can do that, whatever. So I'm telling you, there's no wrong way to eat a Reese's peanut butter cup, and there's no wrong way to end a proof in this class. Just have fun with it, okay? But you don't get to sign off at the end until the bottom line on both sides are same, okay? Now, having said all the stuff on the right, you are not going to have to do that, all right? This is what your proof would look like. Do not skip any step at all. The process is the product. It's what I'm grading, okay? So when in doubt, do not leave it out. Put it in there, all right? And you work straight down. You don't even need to put equal signs. You just work straight down. Now, here's the cool thing about a proof. What if you got to y over x right here and you're like, I'm stuck. I'm at a loss. I know not what to do anymore on the right-hand side. Guess what you can do? You can abandon the right-hand side and jumps over to the other side, in this case, the left side. And you can be like, tangent of theta. Oh, that's y over x. And guess what? Are you done with the proof now? Are the bottom lines on both sides the same? Yes. You could stop right there. As long as the bottom sides are the same, you can work a little bit over here, work a little bit over here. As long as the bottom lines are the same, you're done with the proof. Because what you've done is you've created, again, this logical sequence of steps. You could jump in anywhere and go clockwise or counterclockwise, and it'll take you along that circular path. All right? So as Diamond Rio said musically back in the 1990s, there ain't no road too long when we meet in the middle. You start walking your way, I'll start walking my way. We'll meet in the middle neath that old Georgia pine. We gained a lot of ground because we each gave a little. There ain't no road too long when we meet in the middle. So kind of the same thing here. Work a little bit on the right, work a little bit on the left, and they'll match up. You know that song? Yeah. Okay, good. It's a good song. It's a good band. All right. What if you get down to here and you're like, oh, man, I don't know what 1 times y over x is. It eludes me. And then you go, I'm going to come over here and I don't know what to do, so I'm just going to multiply by 1, because I know it's the same. Hey! Are we done with the proof there? Yes. Do the bottom lines, are they exactly the same? Yes. So again, it doesn't matter as long as the bottom lines are the same. Now, if you like the challenge, it is preferred to try and stay on one side completely. It is preferred. although it is not required. You want to be effective, but then the secondary goal is to be efficient. So it's considered more beautiful to work it exclusively on one side. All right?
So your final line, even though, never mind, answer my own question.
Okay, good. Yeah, the bottom line on the left side, if you don't do anything, is the left side itself. So those are the same. Okay, so anyway, you could prove the other two sets of identities in a very similar fashion. All right? So that's how you do proof. Pretty cool. All right, let's learn another set of identities. These are called the quotient identities or the ratio identities. Interchangeable. Quotient divided by ratio identities. No, that's not what that means. Quotient or ratio identities. Now you have to memorize these. No, you don't. You know why? Because you already know them. You already know them. Here's what they say. There we go. Tangent of theta is sine over cosine. Did we already know that? Yeah, we already knew that. That's how we actually computed the tangent ratio from the unit circle. We took the sine y value and divided by the cosine x value. So tangent is sine over cosine. And similarly, cotangent is equal to what? Cosine over sine. We call those the ratio identities because we write tangent as a ratio of two trig functions. And we write cotangent as a ratio of two trig functions. Now notice what we can already do just with these few sets of identities. I can now rewrite sine over cosine using reciprocal identities. For sine of theta is the same as 1 over cosecant of theta, and cosine of theta is the same as 1 over secant of theta, right? That's what identities are useful for. I can replace sine with 1 over cosecant and cosine with 1 over secant. And now I have a complex fraction. Hooray! So if I stay chain flip, I end up with secant over cosecant. And I have just invented, I wonder if it's ever been invented before, another identity. Not only is tangent equal to sine over cosine, but apparently it's also equal to what? Secant over cosecant. Now, do you want to memorize secant over cosecant? I would not stop you. I can't say, don't memorize it, because then you're going to want to. But you don't have to memorize it because it is so easy to obtain from the fundamental identity by using other fundamental identities. There's all kinds of equivalents, okay? Now, once you've proven its identity, you can actually do all kinds of algebraic stuff. So if you wanted to take the cosecant and multiply both sides by cosecant, you end up with cosecant of theta times tangent of theta equaling secant of theta. That's another identity, okay? I just took the two highlighted parts, multiplied both sides by cosecant. Divides that on the right, leaving secant. Now I have secant, cosecant times tangent. There's another identity. Do you want to memorize that one? No, you don't have to memorize that one because it's easily obtainable from your fundamental identity. Okay, so that's the idea behind the fundamental. They're the building blocks. And so you actually do build with them. You don't just like memorize all the blocks. Okay, sweet. Yeah, go ahead, fire away.
On the proof itself, though, would you have to show, if you came up with secant over cosecant, would you have to then show how you got that?
No, here's the cool thing. All of these identities that I give you are in fact identities. You don't have to like reinvent the wheel every time you want to drive. I'm just showing you the idea of proof. So once you have an identity, you can manipulate it algebraically by doing those typical rules. Multiply both sides by 5, whatever, and you'll get another identity automatically. If you want to prove it because you're not sure, then feel free to go through that process again. But once you know it's an identity and you've proven it, then you can manipulate it after the fact. All right? Now here's what's cool about both the reciprocal and the ratio identities. They work for any power, all right? So 1 over cosecant squared, that's the same thing, bless you, as 1 over cosecant times 1 over cosecant, right? Because that's what cosecant squared means. When it's written like that, it's cosecant times cosecant. Well, what's 1 over cosecant times 1 over cosecant? It's sine times sine, right? Which would be sine squared. So 1 over cosecant squared is just sine squared. And it works with the ratio identities. Tangent to the fifth of theta is tangent times tangent times tangent times tangent times tangent. Each of those is equal to sine over cosine times sine over cosine times sine over cosine times sine over cosine times sine over cosine. So it ends up equaling what? Sine to the fifth over cosine to the fifth. So for the reciprocal and the ratio identities, as long as the power is the same on both sides, it works for any powers. Pretty cool. All right, speaking of proof, let's go ahead and prove this one. We want to prove that cotangent of theta is equal to cosine over sine. We've been using it this whole time. What do you mean to tell me that it might not be true? Prove it. Okay, I'll prove it to you. Now, can we prove it by plugging in a value of theta from the unit circle? Can I plug in like a pi 6 and show that the numbers on each side are the same? Is that a proof? Very good. If you use actual numbers and you plug it in and show that it's true, you've only shown that it's true for that particular number. That's called verification. Okay? If you do that for a gazillion numbers and you create this list of numbers for which it works, that's still not a proof. Okay? No amount of verification constitutes a proof. So how do you prove it for all values? Because you can't physically verify it for all values. You simply use variables, because those variables can then represent any number. All right? So let's go ahead and do it. We'll prove it. First step, draw a line down der Mitte. And then we can start on either side, but which side has more info? Cosine over sine. So because this is a fundamental identity, we're going to have to go subterranean here. We're going to have to use the definition. So cosine is what in terms of x, y, and r? X over r, all divided by sine, which is y over r. We're not going to write the reason, but the reason would be definition of cosine and sine. Hey, complex fraction, right? State change flip, you could do that. So that's x over r times r over y. That would be property of division. Now what happens with your r's? They divide out, okay? And you're left with x over y, and that would be division property again. R's divide out. And now what is x over y the definition of? Cotangent of theta. Is that the same on the left? Yeah. So you can sign it off with something like, heck yeah. Just watch your language. Just be careful. I mean, you can get kind of in the heat of the moment and say something maybe that's a little bit too intense. So, I mean, heck is kind of borderline, right? Keep it clean. You're going to feel victorious after some of these monster proofs that you're going to want to put like freaking animal, yeah. All right? Just be careful. Okay, sweet. Now we're going to learn some new identities that we've alluded to only in previous worksheets. These you're going to have to memorize. These are called the Pythagorean identities, or as I like to call them, the PIDs. These are the PIDs, man. PID stands for Pythagorean identity. Okay? PIDs. The PIDs. Okay? There are 3 PIDs. We have Papa PID, Baby PID number 1, and Baby PID number 2. Papa PID is a single parent, very unimaginative when he named his 2 children. Baby PID 1, Baby PID 2. All right? They fight a lot, that's for sure. All right, this one here is what I call Papa PID. And I use 2 P's in Papa because that's how he spelled his name. Papa John, the pizza guy, 1 P in the middle. All right, Papa PID. Here's what it says. Cosine squared plus sine squared is equal to what? 1. When is cosine squared plus sine squared equal to 1? When? Yeah, we did have it on a worksheet. For what values of x is cosine squared plus sine squared equal to 1? All of them. Every single one of them. This is an identity. It's a replacement of one with the other that's equivalent. So, cheerleaders, next time you go, we're number one. What? We're number one. What? You can now say, we're number cosine squared plus sine squared. We're number cosine squared plus sine squared. And everyone will be like, what the heck? Oh, one. Oh, yeah, Papa Pid. I'm with you. Good cheer. Cadence is a little off, but the meaning is the same. All right. Now, why is this guy called Papa Pid? Well, he's the main one. He's in terms of sine and cosine. Okay? By asexual reproduction, there is no Mama Pid. Okay? He produces two offspring. Okay? If you take Papa Pid, which is an identity, and we'll prove it here in a second, if you divide every term by cosine squared and simplify using the reciprocal and the ratio identities, what do you get? What's cosine squared over cosine squared? 1 plus what's sine squared over cosine squared? Tangent squared from the ratio identity. And what's 1 over cosine squared? Secant squared from the reciprocal identity. Okay, you get baby Pid number 1. 1 plus tangent squared is secant squared. So see why he's a baby? He comes from the papa. It's like a seahorse, I guess. All right? 1 plus tangent squared is secant squared. So what's cool is you can write cosine squared in terms of sine squared. You can write tangent squared in terms of secant squared. Because once you know their identity, you can solve them. You can manipulate it. So if you wanted to take Papa Pid and subtract sine squared from both sides, you get another identity. Cosine squared is the same as 1 minus sine squared. Do you want to memorize that? Say no. No. Because it's easily obtainable from the fundamental identity. All right? Same thing over here. If you subtract tangent squared from both sides, you get secant squared minus tangent squared is equal to 1. And there's another cheer possibility, right? We're number secant squared minus tangent squared. Oh, I thought this was a cosine sine party. I wasn't prepared for secants and tangents. But it works. Now, before we meet baby Pid number 2, because he was born later, we'll simulate that. Is this the same then as cosine of x plus sine of x equaling 1? Can I just take the square root of the left side each term? Is that true? No. No, that is not true. Yeah. So it has to be squared, which is why these are called the what identities? Pythagorean identities, right? A squared plus B squared equals C squared. A plus B does not equal C. A squared plus B squared equals C squared, though. So they have to be squared. All right, so how do you meet baby Pid number 2? Well, if you do a similar thing, asexual reproduction, this time you divide everything through by sine squared, and you simplify using the reciprocal and ratio identities. Let's look at term number 2. What's sine squared divided by sine squared? 1 plus cosine squared over sine squared is cotangent squared. And then what's 1 over sine squared? Cosecant squared. There's baby Pid number 2. 1 plus cotangent squared is equal to cosecant squared. So you can write cotangent squared and cosecant squared in terms of each other. In fact, cosecant squared minus cotangent squared is equal to what? 1 as well. So once you know Papa Pid, which is easy to remember, right? Cosine squared plus sine squared equals what? 1. What's another name for 1? Cosine squared plus sine squared. Of course, you can say it's sine squared plus cosine squared as well. Here's how you remember the baby Pids. 1 plus tangent squared is secant squared. And then all you have to do to get baby Pid number 2 is put what's in front of both of those functions? Cos. Good. So instead of 1 plus tangent squared, it's 1 plus cotangent squared. And instead of equaling secant squared, it equals cosecant squared. That's an easy way to kind of keep them straight. All right? You do have to memorize those. These are wildly used Okay, with reckless abandon. We use these quite a bit, especially in calculus. We use them a lot. Now, just another reminder that if you see something like cosine squared, sine cubed, what are we actually squaring? The whole ratio, right? It's a condensed way to write cosine of x quantity squared, all right? And notice I went back to using x instead of theta. It doesn't really matter, right? Context clues will tell you if it's an angle or a ratio. If it follows a trig function, regardless of what letter you use, it's an angle, right? All right, let's prove this. Let's prove that cosine squared plus sine squared equals 1. And I think we already did this on the worksheet, but it was so long ago. We'll do it again. All right, so you draw a line down the equal sign. And again, that's just to prevent you from cross-contaminating. Because in the process of the proof, you cannot manipulate both sides at the same time. You have to work on each side independently. Once you prove it, then feel free to subtract sine squared from both sides, or whatever you want to do. All right, which side has more info? The left, right. Now, if you want the challenge, start on the right. Kind of like the Big Bang, right? You have a really dense nucleus of 1. And somehow inside there lies the potential for a cosine squared plus sine squared. Let's try it once. If I want to prove that 1 is equal to cosine squared plus sine squared, what do I do next? What do I do from 1? I'm building the house now. I'm going to add 5 and subtract 5. Is that legal? Sure, because I just added a clever form of 0. Is that going to help me get over to the left side? No, I'm not a home builder. I'm more of a yo-yoer, which has nothing to do with building homes, which I should be doing this. So let's start on the other side. Oh, yeah, I could take my yo-yo and swing it around and tear the house down eventually. I might damage my yo-yo, but I could do that. All right, so what you're going to do over here first is write this in expanded form. That's your first step. Your first step is to write it in expanded form. The reason would be expanded form. You don't have to write the reason, though. You're welcome. Now, if you leave off the parentheses there and you just write it like this, then it's what? It's cosine of x squared, and that's wrong, so you'll lose points. The process, remember, is your product. And I will be going through your quizzes and tests with a comb that is very fine-toothed. Teeth. Many teeth. Close together. And I will be looking for any kind of mistake. Okay? Whether it's notational or logical. Now, because this is also a fundamental identity, we must use the definitions. All right? So cosine of x or cosine of theta or cosine of lambda, whatever the variable might be, what is the definition of cosine in terms of x, y, and r? X over r plus sine is y over r squared. And now we have some algebra to do. All right? So that's the same as x squared over r squared plus y squared over r squared. Now here's another strategy. Bless you. And you'll be looking for a lot of different strategies because these proofs, there's not like a single path always from start to finish. It's more of like strategies. I have 2 terms on the left. See that? I need to somehow eventually show that it's equal to a single term. So if you have fractions, in order to get multiple terms that are fractions into a single term, you need a what? Common denominator. We happen to have a common denominator here. But you'll see moving forward that if we didn't, that would be the next step. We want to get a common denominator so we can combine them together into a single term. In this case, though, we just have x squared plus y squared all over r squared. And since we've done this already, hopefully you know what the next step is. What is x squared plus y squared? No. It's not equal to shoot either. It's equal to r squared. It's our Pythagorean theorem. We don't use a squared plus b squared equals c squared. Remember, we call that x and y, and we call that the radius of rotation. So by the Pythagorean theorem, which is why these are called Pythagorean identities, we get r squared over r squared. And of course, what's r squared over r squared? 1. Does the left side look like the right side? Yes. Damn! Canyon. Damn. Canyon Dam. What's that?
I said, are there complex proofs to the point where you have to go on both sides?
Not have to, but we're probably going to have to, because we'll get stuck. But in theory, you wouldn't have to, but you may lose the insight or the path you're taking, and you would jump to the other side. Yeah, we're still we're not even scratching the tip of the iceberg. We're just like, I don't know, what's another allegory that can refer to something that's less than the tip of the iceberg? Like we don't even know the iceberg's there. We're like on the Titanic at night, a few miles out. Like we're not even at the iceberg. Oh my gosh. We haven't even begun to sink yet. Okay. Does that inspire confidence? I will tell you that this is where students tend to either rejoice in delight because it's fun, or they start to sink, like on the Titanic, right? And I will tell you that ahead of time, you can prevent yourself from sinking by memorizing your identities and really, really paying attention to the strategies that I talk about, okay? And then practice. Practice. You get better by practicing. Okay, this reminds me of another joke. You might have heard it. What did the fish say when it hit the concrete wall? Damn. Damn. Good. All right. It's a good one. And it's clean. It's clean, right? Because it's the D-A-M dam, not the other one. The next set of identities, you have to memorize the PIDs because you didn't know those previously, but now you do. The next set of identities, you don't have to memorize because, again, you already know them. These are the even and odd identities, and this deals with the symmetry of every trig function. Every trig function has some type of symmetry. It was on the previous test. There's only two trig functions that are even. What are they? Cosine and secant, because they're reciprocals of each other. The other four are odd. So remember, the consequence of an odd function is negative inputs become negative outputs. If you have a negative x, you could pull it out front. Okay? So sine of negative x is equal to negative sine of positive x. Same thing with cosecant. Tangent and cotangent are also odd. So tangent of negative x is negative tangent of positive x, and the same with cotangent. And then cosine and secant, you could just get rid of the negative. Cosine of negative x is cosine of positive x, and the same with secant. So if you ever have a proof that you're trying to do, and you ever see negative angles, negatives inside, you're going to be using the even and odd identities to bring them out front or get rid of them, depending on whether it's odd or even, respectively, okay? Now, the last set of identities we'll meet today are called the cofunction identities. And I have been alluding to the cofunctions the whole time, right? Sine and cosine are cofunctions of each other. Tangent and cotangent are cofunctions of each other. And secant and cosecant are cofunctions of each other. And again, what does co stand for? Not coterminal, but complementary. And complementary angles add up to how many degrees? 90. 90 degrees is how many radians? Pi halves. So here are your cofunction identities. You do have to memorize because you've never seen them before, but they're easy to memorize if you know what co means. Okay? It means pi halves. So sine of an angle is equal to cosine of the complement of the angle. How do you find the complement of 30 degrees? You subtract it from 90. So it's 90 minus 30. We're just working in radians. So what's the complement of x radians? You subtract it from pi halves. So it's pi halves minus x. So sine of x is equal to cosine of pi halves minus x. And then similarly, the other way around, cosine of x is equal to sine of pi halves minus x. Because sine and cosine are each other's what? Cofunction. And that pattern is identical for the next set. Tangent of x is cotangent of pi halves minus x. Cotangent of x is tangent of pi halves minus x. And then the last set here, secant of x is equal to cosecant of pi halves minus x. And cosecant is equal to secant of pi halves minus x. They all are pi halves minus x. That's how you find the complement of an angle. That is it for your fundamental identities. Memorize them tonight. I may throw a couple of those on your quiz tomorrow just to help buffer the grades. Memorization is easy, all right? Have a splendid Thursday.